Hi, I'm Dr. Tom Calabrese, and welcome to another edition of Insights into Computer Science. This week, we will focus on representation of bits as they travel over our data communications networks. We have already seen how bits of data can be represented on a computer through the use of transistors. These amazing creations have been the catalyst to the incredible development of more and more powerful computers. The typical transistor can switch states in a billionth of a second. That is, switch between on or off or create zeros and ones. That means that transistors are really fast. Transistors are also really small. With today's technology, we can design logic that can place 2 billion transistors into a space of only 1 square centimeter. Transistors are constructed from materials known as semiconductors, things such as silicon. The transistors and the conducting paths are printed on silicon wafers, known as integrated circuits. This technology has resulted in very small, very fast, and very inexpensive technology. Moore's law states that the number of transistors on a circuit board has been roughly doubling every 24 months. As of 2016, it is estimated that it would be possible to have 10 billion transistors on a circuit board. Of course, maintaining that level of growth will be impossible, and recently chip manufacturers began reporting limitations because the separation of the transistors on a chip is now about 50 nanometers or less, which creates signal interference and improper operation of the chip. So the question is, will this be fixed? Probably, and growth will continue, I'm sure. But someday a practical limit will be reached. Bits can also be stored magnetically or photonically. One of the things modern computer scientists have to concern themselves with is computing over a data communications link, the network. We all know that it can be done, obviously, but how many of you really understand the nature of data communication technology and the many byproducts that technology has brought us? Well, in the 1940s and 50s, there were two amazing engineers that worked for the US government and eventually for Bell Laboratories in New Jersey, Harry Nyquist and Claude Shannon. Each of them had a very interesting career that eventually led them to tackling some of the most interesting engineering problems of their time. Bell Labs was the research and development wing of the Bell operating companies. The history of Bell Labs is fascinating and interesting to review. One of the many developments that Bell Labs is responsible for is the digitization of voice. In particular, Harry Nyquist first examined the relationship between the voice analog signal and its digital counterpart. The digitization of voice signals allowed for voice signals to travel further without being affected by attenuation. Attenuation is the decay of a signal with respect to both time and distance. Prior to Nyquist's work, a signal would travel many miles over the phone wires, and the quality of that signal would decay, and the voice quality would be lost. In other words, you wouldn't be able to recognize the voice of the person you were talking to. To make matters worse, the engineers of the time tried to combat this loss of signal with amplification. This was bad because it took the distortion created by the decay and made it louder. In other words, it made a poor quality, noisy call worse. So, can you hear me now? Not so much. Nyquist discovered that if he followed the analog pattern with a step function, he could approximate the original signal and encode the signal as a 1 to step up a standard unit or a 0 to step down a standard unit. By doing this, he could create a bit pattern that could be sent between devices, then decoded at the remote end to reproduce the original signal, without really worrying about the effects of attenuation. Not that the signal at the far end would be the exact signal, but it would be a fair approximation of that original signal. This significantly improved the quality of the voice of the parties on the call. Nyquist did this by encoding the ones and zeros into the carrier signal. The carrier used by the phone company was, and still is, a simple sine wave. That wave has two sampling periods, here and here. If the curve is smooth, we say that it contains a zero. But if we introduce a disturbance in the curve by adding additional frequencies, we create something different from the smooth curve, which is easily recognizable as a 1. By doing this, we realize that the attenuation now has less effect. Nyquist then captured this capacity calculation in this formula, which states that if we take 2 samples per cycle and multiply that by some number of cycles per second, and in the case of voice, it's 4,000 cycles per second, and multiply that by 1 bit per sample, we create 2W, 2 times W, or the 2 times the frequency in the bandwidth, bits per second. And this is really amazing. Nyquist had discovered the concept of modulation and demodulation, or the basics of a modem. Now, Claude Shannon was a co-worker of Nyquist, and he was looking to take this theory to the next level. In a lab, Shannon observed that the amount of clipping and noise introduced through the digitization process could be reduced if they were using a more discriminating receiver. What is that, you ask? Well, that means that Nyquist used a simple up or down movement associated with a single bit, 1 or 0, respectively. Shannon suggested that they could represent more bits during each sample period, and so they could do things like move up a little or move up a lot, or show no change, or down a little or down a lot, and so on. Essentially, he wanted to create a better ruler. Shannon suggested that they could represent 256 different signals, far more discriminating, meaning to notice change, than Nyquist's 2 simple signals of up or down. Because of this, Shannon was able to rewrite the Nyquist formula to account for this change. This formula states that capacity in bits per second equals the same 2 samples per cycle times the same W cycles, or 4,000 cycles per second, but enhances the formula by adding log base 2 of the number of signals, call it S. For those of you who don't use logs all that often, essentially what it is asking is the question, what power must I raise 2 to get the value of S? So in this case, 2 to the what is 256. Well, that's 2 to the 8th is 256. What does that mean? Well, he created the means to encode a byte of information, 8 bits, in a sample, and created a capacity, if you do the math, with 4,000 as the frequency or bandwidth, of 64,000 bits per second when using the standard voice carrier of 4,000 cycles per second. This is known by the phone company as a DS0, and is the standard bits per second required to make any non-compressed phone call even today. So why worry about this, you ask? Well, first, data communications and computer science are closely related fields, and it's good to know how your information is represented as it traverses the many phone lines that make up or interconnect the web. Second, this codec-based technology that Shannon created is the basis of how computers represent pictures, sounds, and videos today. Your computer uses codecs and video processors to make the interesting applications that you're so fond of and probably take for granted as to how they were created. Now you have the knowledge necessary for understanding how your computer represents sound, pictures, video, and even simple data. Believe it or not, this important lesson sets the groundwork for you to be able to create algorithms that allow users to play games, watch videos, record music, play music, record videos, and even create holograms. So until next time,